Okay, so we're going to start our lessons on planes. Okay, so planes are going to be a two-dimensional thing in 3 dimensions. So recall that in 2 dimensions, 2 non-collinear vectors can span the 2 dimensions. Okay, so non-collinear means they don't lie in the same line. They're not scalar multiples of each other. Okay, so in R3, in 3 dimensions, these 2 vectors can span a plane. Okay, so I've drawn a picture here of a plane that is spanned by the vectors a and b that I've given here, -3, 2, -3, and 3, 1, -1. So what I've done is I've drawn the x, y, z axes, and I've plotted vector a by going 3 back on the x-axis, 2 on the y, and -3 on the z, and that gives me vector A. And vector B is going to go 3 on the x-axis, 1 on the y, and -1 on the z to give me this vector B. Taking these 2 vectors, they can form a parallelogram here. Okay, so made from these dotted lines here. Now, if I take scalar multiples of these vectors, so something times a plus something times b, if I use integer scalar multiples, then I get all these other pieces here. So here's 2a plus b, okay, would give me a vector to the from the origin to there, or sorry, to there, okay, and I can go back these sheets here, so I can extend it beyond the one piece here. Okay? So these vectors, taking scalar multiples and adding them, will get us vectors that go from the origin to a point on the plane. Actually, vectors that are on the plane for these ones, because these vectors start at the origin. Okay, so it's like a wire diagram of what the plane would look like in the 3 dimensions. Okay, so here this vector from the origin to here is going to be 2a plus 2b. This vector from the origin to over here is going to be -a plus b. Okay, so any linear combination of a and b give a vector on the plane. This basically means that r equal to sa plus t times b is a vector on the plane. And this is a vector equation for that plane, okay, that type of plane. Okay, so planes of the form SA plus TB will go through the origin. Okay, so when S equals T equals 0, you get R equal to the 0, 0, 0 vector. So that's R equal to SA plus TB will go through the origin when S and T equals 0. Okay, so these vector equations of planes are planes that go through the origin. Now, for planes that do not go through the origin, you need to translate them away using some vector r0. Okay, so this vector r0 that translates them away from the origin is not parallel to the plane formed by A and B. So it can't be parallel to that plane, which means it's not a linear combination of A and B. If it was parallel to the plane, it would just be translating it along its own plane, which means it still goes through the origin. Okay? If it's not a linear combination, then R0 cannot equal SA plus TB for any S and T. Okay, so now we're going to look at translating this. Okay? So translating this, well, let's take that same plane. So I've got the A and the B vector, A and B, and I'm going to translate it away from the origin with this vector R0. R0 I've chosen so it's not a linear combination of these two. Now, this picture is going to look a little bit complicated at first, but hopefully I can explain it through. Okay, so here we go. Here is a picture of the plane that is parallel to A and B, so spanned by these 2 vectors, and is translated away from the origin with this. So it goes through the point 1, 2, 5. Okay, so first what I've done is I've taken that vector r naught, 1, 2, 5, and I've plotted it first. So here's the vector r naught, 1, 2, 5. So I go 1 in the x, 2 in the y, and 5 in the z, and I get that point. So r naught is this blue vector here. Because I'm translating it away from the origin that much, what I'm doing is now making a new set of axes in blue here. So the x, y, z, and I'm now going to plot the a and the b vector up here. Okay, so there's the a vector, -3, 2, -3, and here's a b vector, which is going to be 3, 1, -1, so it's right here in red. And choosing scalar multiples of these, so linear combinations of those vectors, will get us this wire diagram that we have here. Okay, and this produces a plane in 3 dimensions that goes through that point. So that's like the anchoring point. Okay, it used to be the origin. Now when s and t equals 0, you get this. And the vector equation of that plane is going to be of this form: r naught plus sa plus tb. A and b are now the direction vectors. Okay, and the vector to a fixed point on the plane is r naught. So the fixed point of the plane is p naught, and r naught is the vector to that point. For this specific plane, we've got r equals 1, 2, 5. Okay, that's the r naught, and here's the a and b vectors put in. Okay, so that's that plane. Now the parametric equations, well, we can just take the x coordinates of these. Okay, so parametric equations is going to be x equals x naught plus sa1 plus tb1, y equals y naught plus sa2, tb2, and z, and so on. Where r naught is x naught, y naught, z naught, and a and b are broken up into components a1, a2, a3, b1, b2, and b3. Okay, so that's going to be the components of those. For our example, here's the parametric equations. Okay, so we've got the parametric equations for these ones. These represent x naught, y naught, z naught, the a coordinates, and the b coordinates. Okay, and so we have an example here. So determine the equation of the plane that contains the point a1, -3, 4, and is perpendicular to the vector v, -7, 1, -2. Okay, so we know how to find vectors that are perpendicular to a given vector. We just take 2 of the coordinates, flip them, change one sign, and make the third one 0. So take the 7, 1, flip it, and make that 7 positive. Then take another one, the other 2, the last 2, flip those, and make the 2 positive. These 2 are not going to be collinear because of the 0 coordinates in the different spots, and they're both perpendicular to v. So these would be our direction vectors. And we have it going through the point A, so our vector equation would be r equals OA plus SA plus TB, and here are the values that you plug in for that. Okay. A second example, determine the equation of the plane that is parallel to the triangle formed by A, B, and C and contains the point D, 6, 5, 4. So if it's parallel to that, then we're going to have A equal to AB is one of the direction vectors. Okay, so figure out AB using 2 of these points from the triangle. And B equal to AC is going to be another direction vector. Okay, so AB and AC could be the direction vectors. It's got to be parallel to that triangle, so those are direction vectors. But it has to go through this point. So this point's going to translate it away from the triangle, not going to contain the triangle. Okay, so OD plus SA plus TB, and here are some of the coordinates that you plug in for that. Okay, and a third example is where does the plane this intersect the x-axis? Well, a solution for that is on the x-axis, y and z equals 0. So if we know y and z equals 0, then we can just set those 2 equations equal to 0 and solve for s and t, 2 equations, 2 unknowns. Okay, so we set z equal to 0, and we can immediately solve for t because there's no s in it. Set y equal to 0, okay, and we can sub in the t value in for t, and then we can solve for s. We solve for s and t. Okay, you may want to pause the video to see if you can do this. Let's follow it through. And then we take those two values, plug it in for the expression for x. And we can solve then for the value of x. And we get, by subbing in these fractions, we get x equal to -5. So that is the x-intercept of that plane.